So here's another insight from this analysis. So what actually happens at the moment of fluidization? Like at one moment, the sand bed is solid, you can stand on it, it's there. And then a little bit later, it's all like a liquid, it's fluid, you can move your fingers through it easily. But what happens in the transition? And this transition, I feel like is worth some more research, because some funny things must happen, especially once you think about the fact that ultimately there's dirt in the filter. And so there's actually head loss as water is trying to flow through the pores of the filter as you're trying to fluidize it. And my best guess is that when you start pushing water quickly up through sand, at the very first instant in time, what happens is the entire bed lifts a tiny bit. And once it lifts a tiny bit, then the bottom of the bed can fall and can free fall, and then the fluidization begins progressively up through the bed. That's my bet as to what happens. And it started with that initially you had to actually lift the bed a tiny bit. And that matters because that means that in our filter system where we have lots of pipes in the bed, initially you're going to put a lot of force on all those pipes because you're trying to lift that whole sand bed, and the pipes that are in the bed are trying not to move. And so you'll apply a lot of force to those pipes right at that transition. And we have demonstrated this. We have broken things inside of filters because of not realizing how strong that force was. And then another one, sand will stratify if there's even a small range of sizes. So let's look at that in the next slide, I think. No, one of the next slides. We'll come back to that. So it's important that all the sand be close to the same size. We can also do one more calculation with this where we have Carmen-Kozeny equation giving us the head loss as a function of velocity, the approach velocity. And we have this equation that gives us the head loss that you must have in order to fluidize the sand bed. And you can set those two head losses equal. And you can solve for at what velocity do you get just enough head loss to fluidize the sand bed. And that's a nice equation because it gets you the minimum fluidization velocity. And in order to fluidize a sand bed, you have to be applying at least that much flow. More than that, if you want to actually get that bed to expand a little bit and be a little more vigorous in its mixing. So this last equation, I show that there's an effect of kinematic viscosity, and you're saying that means there's an effect of temperature. So what does that mean? What happens to the minimum fluidization velocity if it is really hot and the water temperature is high? Then the viscosity is smaller, and that means I have to increase the fluidization velocity. Or sorry, the fluidization velocity increases. So in order to fluidize it, I have to push more water through that filter. So that means if you're designing a filter, you better design it so that it fluidizes really well, even when the water is warm. The diameter I'm focusing on there is what happens if there's different diameters of sand grains in your bed. What will that do to the fluidization velocity? And what's clear is it's a really strong effect. If you would double the sand grain size, it would multiply by 4 the fluidization velocity. So that's another reason why having uniform sand grain sizes in a filter bed is really, really important. I used to always go to the front of the class and draw this on the board, and I realized, oh, I'm not going to have a blackboard today. So this is a graph showing, and I forgot to animate it, darn. This is what happens as a function of velocity up through a sand bed. So there's the sand bed hanging out there on the right, and we're slowly going to increase the flow of water up through that sand bed. And we're going to measure the head loss, the pressure drop that's happening across that sand bed, and we're going to plot it. So under conditions of zero flow, if there's zero flow, there's no head loss, and so head loss starts out at zero. And then as we increase velocity, the Kármán-Kozény equation applies, and we're just increasing the filtration velocity. And the Kármán-Kozény equation says that the head loss is going to be proportional to the velocity. So we get this straight line. And then we get to the place where the head loss is equal to the depth of sand. And at that moment, assuming that it's silica sand, it completely changes. Now, the sand bed fluidizes, and from that point on, it doesn't matter how much water we push up through the sand bed, the head loss is the same. Now, I just said something which seemed a little bit bold. I just said that it doesn't matter how much we increase the flow rate up through the sand, it'll always have that same head loss. And you learned from me that you should always think about extreme positions and see what happens. So do you think my statement was right? If you just keep on increasing the velocity of water going up through, you get this tank, it's got sand in it, you're pushing water up through that sand faster and faster. And I'm saying that it won't change the head loss because it's always a force balance of that you have to be suspending all that sand. But what happens eventually if you keep on increasing the velocity of water up through that sand? Anyone, be bold. Can you think of something else that changes if I keep on going faster? Like, in your mind, did you send the water up through that sand really, 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 really fast? Like, what happened in your mind? What did you see? What did you see coming out of the top of the tank? You've done the experiment in your head, right? Anybody see sand coming out of the top of the tank? Yeah, because at some point, the velocity of the water exceeds the terminal velocity of the sand. And so the sand is going to go out. So this plot is missing another stage where eventually that black line has to come back down because there's no longer any sand in your tank. But there is this region where it's fluidized and it's expanding a little bit, but it's not coming out of your tank yet. And at that point, the head loss is constant. Over that range, it's constant. Anybody have a question about that? Because this plot is, I feel like it's a mind-blowing plot because I've always understood that head loss increases with flow rate, right? And now I'm showing you a plot where there is a section in the plot where the head loss doesn't change, flowing through porous media as a function of flow rate because it's fluidized. I feel like we already did this effectively. This is about the fact that we've got sand grains that vary by a factor of 2 in diameter. And if the sand grains vary by a factor of 2, then the fluidization velocity varies by a factor of 4. So we'd like to have more uniform sand. And maybe I will just present kind of the nature of the problem now that we're trying to solve. So I've given you some background on what's going on inside filters, concept of porosity, minimum fluidization velocity, head loss through clean sand. And now we have this problem that we could use slow sand filters, but I previously made the case that slow sand are interesting, but they're big because they're slow. And because they're big, they're capital intensive. And because they don't have any way of automating or mechanizing the cleaning process, it means that they're going to be cleaned by hand. Although granted, in London, where they have 80 hectares of slow sand filter beds, imagine the market value of that land, 80 hectares of land in London that is tied up in slow sand filters. And when they clean their slow sand filters, they have made very light, big tire carts that motorized carts that can go out and scoop off the sand and carry it off the sand bed. But in general, you'd be doing it by shoveling. So we're not so keen on slow sand filters. And rapid sand filters are cool. They're so much smaller, so they're going to be cheaper to make, but they require pumps to backwash because we need a lot of water going up through that sand bed in order to fluidize it and wash the dirt out. So we have neither of these options is good. There is a group that has invented a nice alternative, and it could be that this has happened on multiple places on the planet, but CEPIS is one of the groups out of Peru in the 60s, I believe, had a very nice system, and I'll show it to you, of a set of 6 filters that work in parallel and then work together to backwash one of the filters without using pumps. But this is definitely a call for invention. So this is the CEPIS system. There's 6 filters in a set. You can see the 6 filters there. And they have those 6 filters working together. And when they want to backwash one of them, they actually take the water from 5 of them that are still filtering water, and they use the water from those 5 to provide water to backwash the 6th filter. And they're able to do that without using any pumps. The dilemma is, in any case, backwash water has to be clean water. It takes a lot of it, and a lot of it fast, because the backwash velocity is high. And so these are the 3 choices. We could pump it from a clear well. That's what's done in most water treatment plants. The set of 6 filters working together, or we could have filtered water stored at an adequate elevation. So we could pump it, and that's what's done in most places. If you pump it, then you also need to have a reliable electricity source, which means in most places that would mean you have to add a generator, and now you have to maintain that generator and keep it operational as well. And in many parts of the world, electricity is sufficiently intermittent that this becomes a real maintenance issue. Here are those 6 filters working together. I don't want to go into this in great detail, but you can see in the bottom, in this schematic here, that 5 filters have water going down through them, and there's the water on the bottom of those filters is all connected together, and so the water underneath them is shared and is going over to the 6th filter. And in the 6th filter, they opened up a valve that allows it to dump its water off of this trough. And so the water level in that filter drops to that trough. And now there's enough elevation difference between the filters that are filtering and the filter that is being backwashed. There's enough elevation difference to do 2 things. That elevation difference has to be enough to push the water through the filters that are filtering, and push all that water through the one filter that is being backwashed. And so this height here has to be the head loss in through the beds that are working to filter, plus the head loss required to backwash a filter. So that's a nice system. And then there's this question, well, what happens if you try to do this for a small community? And I do the math here, but the big concept is I've got 6 filters. And in order to backwash them, I need 5 of those filters to be getting enough water to then backwash the 6th one. And what if I'm in a drought and the water supply for my town is cut by 50%? What happens? And it turns out normal backwash velocities are on the order of double a fluidization velocity, which means that if you're at half the flow, you might not even fluidize the bed at all, which means you have no ability to backwash at all. So if you were going to build this system of 6 filters working together for a small community, and you learn that this community has low flow periods where they have less than 50% of the design flow for your plant available during summer droughts, what would you do? You see the problem? If we design one set of 6, come drought, we won't even be able to operate those filters because we won't be able to clean them. So what do you do instead? Yeah, Ravi's got it. You're going to design 2 sets of 6. And now you can operate at half the flow rate and you can still backwash your filters. So we just came up with this uncomfortable conclusion. I don't know if you felt the uncomfort or not, the discomfort. But operating with one set of 6 is very risky because you can't handle periods of low flow. And to solve that, you have to double the number of filters. And so now all of a sudden for a small community, the minimum number of filters that you can use, you could easily argue is 12 filters. And when you propose that to a small community that you're going to build 12 filters to solve their problem, and each of those filters has valves and each of them is a little concrete box, all of a sudden you're beginning to look like a crazy engineer. So that's where I'm going to leave it as, oh my goodness, there are no good solutions. We're left with either we buy a generator and a bunch of pumps, or we have a crazy number of filters.